Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 4th, 2026, about 5 days ago. It challenges the industry standard for fine-tuning large language models, arguing that the core mechanism of proximal policy optimization is structurally mismatched with large vocabularies, and proposes a more stable alternative called divergence proximal policy optimization. The paper is titled Rethinking the Trust Region in LLM Reinforcement Learning, and as we'll see later, the resulting improvements in training efficiency are quite promising. Figure 1 illustrates the core innovation. On the left, the equations compare the update rules. The blue box highlights the standard proximal policy optimization mask, which clips updates based on the ratio of new to old probabilities. The authors argue this is noisy for rare tokens. Below that, the green box shows the proposed divergence proximal policy optimization mask, which constrains the arithmetic difference, or total variation, between policies. The chart on the right confirms this works. On the AME24 benchmark, the red and green lines for the new method clearly outperform the blue and orange group relative policy optimization baselines. Well, Figure 2 investigates the root cause of this instability using a QN3 model. The left scatter plot tracks the probability ratio, which is the core metric in proximal policy optimization. Notice how, for low probability tokens on the far left, the ratio is incredibly volatile, scattering vertically due to seemingly minor numerical noise. This triggers aggressive clipping that freezes learning for rare tokens. In contrast, the right plot shows the total variation divergence used in the new method, which remains much more consistent and bounded across the entire distribution. Moving on to Figure 3, we see the consequences of that volatility on training performance. The first two charts track rewards and benchmark accuracy. Notice the brown and pink lines for the divergence proximal policy optimization variance. They climb steadily and stay high. In contrast, baselines like the purple group relative policy optimization line suffer catastrophic collapse, dropping to near zero. The third panel reveals the culprit by plotting the training inference mismatch. While baselines shoot up vertically, showing the model drifting wildly from its generated data, the new method keeps this divergence flat and strictly controlled. So, Figure 4 isolates a crucial design choice, whether to anchor the trust region to the original rollout policy or to a recomputed one. The left panel tracks training rewards, where the green line, using the proposed rollout anchor, remains stable and converges to high accuracy. In contrast, the blue line represents a decoupled approach that recomputes the reference, and it eventually crashes hard. The right panel explains why. That blue line shows the policy drifting far away from the rollout distribution, confirming that anchoring to the original rollout is vital for stability. Alright, moving to Figure 9, the authors extend their evaluation to larger scale experiments with different model architectures. This figure tracks the evolution of test scores on the AME24 and 25 benchmarks during training. The first two panels on the left show the QN330B model, where the blue line for the group relative policy optimization baseline clearly destabilizes and crashes. Then, the last two panels on the right show the QN38B model. Here, even the orange line for the CISPO baseline suffers a sharp drop in the final chart. Throughout all these tests, the red and green lines for the proposed divergence proximal policy optimization remain robust and stable. Well, to ground those results, Table 1 lists the exact hyperparameters for the 5 experimental setups. The columns display the different architectures, including standard mixture of experts, a version with rollout router replay, and a dense baseline. Notice the second numeric row. The maximum response length is set to over 16,000 tokens for the MOE models, enabling the long chains of thought needed for reasoning. Finally, the far right column shows that the LoRa configuration required a much higher learning rate of 1E-5. Wrapping up, two takeaways stand out. The standard probability ratio in proximal policy optimization is fundamentally noisy for the long tail of large language model vocabularies. By switching to a direct divergence constraint, the proposed divergence proximal policy optimization fixes this instability and prevents training collapse. This suggests a more robust standard for future model alignment. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.